So, welcome everyone. Let's have a look at problems 11.1, 14.1, 15.2 and 16.2 together, because all these problems are dealing with the vertical dynamics of an aircraft, and these are modeled by these state space model matrices which are given to us. Now, before we start looking at the control problem, I'd like to very briefly at least give some vague interpretation of this model and have some idea where this model comes from, and give some meaning to the states and the control inputs. So let me bring a sketch. So on the right now you see a schematic or a sketch of the different states and the control inputs that are given to us. So let's first rename these states to have some understanding. So x1 is the relative altitude, which I represent by z in this figure. The second state and the last states, the fifth state, are the forward and the vertical velocities. The third state is the pitch angle theta, and the fourth state is its derivative, theta dot, also called as pitch rate. Now these can be seen here in the sketch. I'd like to have a small disclaimer that I could not really find a derivation of this model, and so we now take this model at face value without going into the physics and just treat the problem as a control problem given some state space matrices. So the control inputs which are given here are represented in the sketch as u1, which is the spoiler angle, u2 as the forward thrust, the forward acceleration, and u3 as the elevator angle. Now beyond this we will not go into the details of the physics, but if any one of you has a good derivation, I'd be happy to understand this from you so that we could include it in the next year and so on. So we're given this model. Now let's have a look at problems 11.1, 14.1, 15.2 and 16.2 together, and let's see what they are saying. So here you see the problems on the screen. Now let's have a look at what these problems are asking us to do. So we're given the aircraft model that we just discussed, that's example 11.1, along with a Simulink file which also does the modeling, and then we are asked to design an LQG controller by using the h2syn command, which is really a command that gives us a controller that minimizes the h2 norm of the closed loop plant. In order to do that, we need to build a generalized plant so that the h2 norm of the closed loop plant corresponds to an LQG cost. We will see how that goes, and then once we have designed this controller, we have to test it for a reference step input, and keeping a track on the force or the control input. So this is essentially a design task, the LQG design task or an H2 design task. In problem 15.2, again we have to consider the aircraft model, where now two designs are given to us, and we have to understand the meaning of the sigma plots or the singular values of the closed loop for different controllers or these two designs and interpret them. So this is an analysis task with the help of sigma plots. Now 14.1 is also very similar. Again, consider the aircraft model, plot the singular values of the closed loop for an LQG controller, which could be chosen as either 11.1 or 15.2, and then interpret the sigma plots or singular values In 16.2 we have something different. We are asked to first find the closed loop sensitivity. We will see what that means. You've already seen in the lectures, but we will quickly recap what that means, and find the best and the worst input directions, again based on the sigma plots. So essentially this is again analysis once we have a controller. Now for the design task in 11.1a, we are asked to design an LQG controller by using an h2 syn command. So let's quickly recap how the LQG control problem can be recast as a problem of minimizing the h2 norm of the closed loop. So let's write down the LQG problem first. So that's our LQG problem. Now let's also try to write down the H2 problem, which is to minimize overall controllers K So that here is our H2 problem. And now the idea is to pose the H2 problem such that it solves an LQG problem. First of all, you can see that the costs look quite similar, except that we here have U transpose RU plus Y transpose Y, and here we have Z transpose Z, where we have this Z. The input here is D. So the whole point is to somehow design this G such that the H2 problem is identical to an LQG problem. So let's see how to do that. So here you have a semi-filled block diagram. Let's try to see what is G exactly here. So if I call this thing, oops. So if I call this thing G, it has an input D, an input U, an output to the controller that is coming here, and Z here. So the idea now is to fill in these empty blocks so that these two problems are identical in cost and in constraints. So and you can check yourself, and I think it's already there in the notes, that if I set this as that one would be R. So if we do that, then we have the same problem. We can check that by seeing that now Z, let's have a look at the cost first. So Z now is nothing but R raised to half U and Q half X. So that would give us Z transpose Z as X transpose QX plus U transpose U. So you can see that with these two blocks your cost is now matching, because Z transpose Z is now here Y transpose Y plus U transpose RU. Note obviously that Q here is C transpose C, so I would have C transpose CX plus U transpose RU, which is then Y transpose Y plus U transpose RU. So the cost is done. So once we have the cost, let's also now look at the constraints. In the in the H2 problem, we have to be I delta of tau. So that just means that the expectation of W transposed, so now W is the so if you now compare these two problems again, W is the disturbance entering the state equation, which is this one here, and now that is nothing but D passing through this QE half 0. So we would have this given by QE half 0 D of T times T of T plus tau transposed QE half zero, which is nothing but, because QE is a constant matrix, you can pull in the expectation inside, which is then nothing but QE delta of tau. Similarly, you can try to show that V of t we have t plus tau. Expectation of this is nothing but re delta of tau. So in order to see that, you just have to look at where v is entering. So v is entering at the output, so that would be here, and this v is nothing but d passing through 0 re half, and you can check that again that this is true. So once this is true and this is true, then we have that the constraints are matching. So we had this and this matching with this, we have the cost matching, and we also have the state dynamics matching, because that's how we get these A, B and C matrices. So we have shown that we can solve an LQG problem by solving an H2 minimization problem. So let's look at the Matlab code where this is being built, but before we do that, let's also represent this compactly as here now. So that's our generalized plant, where the U is coming from the controller and Y is going back to the controller, and D and Z govern the performance channels. So that's our model, and the model matrices for our generalized plant can be simply written as this. So A GP is A, B generalized plant is this, C generalized plant would be this, and D generalized plant would be this. So this is the function given to us, make LQG plant. It takes in as input model matrices, the open loop model matrices A, B, C, D, and the tuning knobs R and RE, builds this generalized plant, and returns the generalized plant as a state space matrices. Returns the generalized plant as a state space model by building it here. Now QE is taken as BB transpose, which is usually a starting choice, and RE is taken as the input of this function, so RE needs to be tuned. And similarly Q is taken as C transpose C, which is also the choice here, because we have in the LQG cost Y transpose Y, and we saw that to get the same cost here, Q should be chosen as C transpose C. Now you can check, however, that the generalized plant that is returned here is not exactly identical with this one, because you can have multiple generalized plants that work. So for example, you could switch the order of QE and still have the same generalized plant, and I encourage you to have a look at this. Another difference is to have a minus C here, so a minus C here, which is also there in the notes. Again, that does not really matter, because either you can pull the minus sign inside the controller, so if you have a minus sign there in the generalized plant, the optimal controller is without a minus sign. If you don't, then the optimal controller would be with the minus sign, so that's also really not a problem. Also, one more reason why this is not a problem is because the disturbance D that is entering the output or the measurement is zero mean, so in expectation that averages out, and the negative sign here does not change anything for the closed loop especially. So now we turn our attention to the tuning knobs. So we have, because Q is chosen as C transpose C and QE is chosen as PP transpose, we have two tuning knobs at our disposal. One is R and one is RE. So R governs the cost of control. So higher the value of R, costlier would be the control, and the optimal controller K would use less control effort. On the other hand, if R is very small, that would mean that control is cheap, and the optimal controller would then try to use higher control effort to get more or better closed loop performance. RE is the covariance of the measurement noise. So it's usually used as a tuning knob in the sense that if we have a higher value of RE, that would mean that the measurement is noisy and can't be trusted. So the observer or the implicit observer that we get out of this H2 design would be slower. And on the other hand, if we have a lower value of RE, that would mean that the measurement noise is rather low and that the measurement Y could be trusted, and that would mean we can push the observer poles more to the left. Yeah, that's the intuition behind the tuning knobs. Now another aspect before we go to MATLAB is that we're given a tracking problem, whereas the LQG or the LQR problem is a regulation problem. So the LQG problem, also LQR, are regulation problems, or in other words, given a non-zero initial condition, we want to find a controller U that minimizes some cost. So there is no reference present in the cost. In order to convert, or in order to use the controller that we obtain from a regulation problem to a tracking problem, we typically use this architecture. Now, because the LQG problem, the LQR problem, was not a tracking problem and was rather a regulation problem, when we use a controller designed for a regulation problem in a tracking loop, we have to do some analysis a posteriori to check the tracking performance. So let's now have a look at the Matlab code quickly to see how this is all being done. So here you see again the file that you should have from the link and from std_ip. So we first define the model matrices, we get the sizes of the control inputs and the output to the controller. So nmes and ncont are basically the sizes of sizes of y and u respectively. Then we design we define the tuning knobs r and re. Then we make the generalized plant, which we already saw, and then we execute this command h2syn to get the controller back. Now, as we just saw, once we have the controller, we put it in a tracking loop by using this command feedback. So that is this loop. Note with a negative sign that I missed. And then we define these two transfer functions, r to y and r to u. So let's run this. For the step input that was asked in problem 11.1, so if we go up, we have to test it for this step input on the first channel. So as you can see that this is the output response. States 2 and 3, the outputs 2 and 3 are going to 0, whereas the first output is converging to 1. The control inputs are shown here with u1, u2 and u3. The constraint on u3 was that u3 should be less than 20. This is far less, so we could perhaps get some more control action that we can do by reducing r. So I try now r as 1e minus 3. Note here that we're already penalizing u3 much lower than the other two channels. So you see that the rise time is much lower now, and the control input is higher in absolute value than in the previous case. And now you can play around with this. So I think you should get an intuition behind the tuning knobs R and RE, and that's basically the motivation behind 11.1. So now we want to do analysis, or rather frequency domain analysis. So let's quickly look at seesaw systems first, and let's very quickly review border plots. So if we had a single input single output system G, and if we looked at the border plot G, which perhaps looked something like this. So this is the frequency axis, and on this axis we plot G omega absolute value. What this would mean is that if I have now an input at some low frequency omega, a sinusoidal input, my output will also be a sinusoidal wave, perhaps with some shift and with an amplitude shown by the border plot or the border magnitude plot. And in this example, if we have this close to 1, so 0 dB is just 1, this border plot would mean that for lower frequencies my output amplitude will be close to 1, whereas for higher frequencies, somewhere here, my output amplitude would drop to a very low value, which would mean that if I had a very high frequency input, that would be attenuated. Now for MIMO systems, we have the notion of directionality. So for our problem at hand, now we have a MIMO system which is this. This can be then represented by a closed loop plant with an R and as an input and Y as an output. So this is a 3x3 system. So GCL of J omega is now a 3x3 transfer function and let's try to see what the border plot of this plot looks like. So let's have a look at the border plots first. Now we get because we have a 3 by 3 3 input 3 output system, we get 9 border magnitude plots. So let's see what these border plots mean. I have a 3 input 3 output system, and the first column of these border plots mean that if I have an input u given by so if u is sine omega t 0 and 0, my output y would be so let me call this phi 1. So if I have an input sine omega t 0 0, my output would be for that frequency. So for example, let's pick one frequency omega 1. If I have an input sine omega t 0 0, my output would be sinusoidal frequencies, perhaps shifted by different phases along all 3 different channels with the same frequency, but with an amplitude given by these 3 border magnitude plots. Similarly, if then I had an input of 0 sine of omega t 0, I would get this one, and if I have an input along the 3rd channel, I would get this along the output. So this is only the amplitude information. The phase information I've not shown here. That would be in the complete border plots. I've plotted here only the border mag or the border magnitude. Now note that we've only considered the 3 canonical directions, that is 1 0 0 0 1 0 and 0 0 1 in these border plots, but there could be a combination of these directions which could cause a higher amplitude sine wave at the output. And in order to address this, we have singular plots or singular value plots or sigma plots. This is where sigma plots come in. So you see now the sigma plots for our closed loop. Note that these are for the closed loop plot from R to Y. So maybe let's quickly also recap what we mean by sigma plots. We have a 3 by 3 transfer function like we saw above. Now In order to have these sigma plots, what we do is we fix a frequency g of j omega. That gives us a complex matrix. We can do a singular value decomposition of such a matrix to obtain these three matrices V, sigma and U, where sigma is a diagonal matrix of the same size and dimension as G, and sigma max for this particular frequency is then nothing but the maximum of the diagonals of sigma of j omega. So for each frequency we do an SVD and we get the maximum singular value. Also then for each frequency we get the direction, the input direction corresponding to this maximum singular value and the output direction corresponding to this maximum singular value. And that means that if I had an input along, so let's say for an omega we get u1 of j omega as the direction corresponding to the maximum singular value. We would get then times sigma 1, that's the output, or I can also call it sigma max. I show j of omega dependence here because the directions and the values might be different at different frequencies. If u is a sinusoidal input with unit amplitude, the output y will also be a sinusoidal input. That is clear because this is true for any linear system with shifted phases along different channels, but with an amplitude whose norm, so let's call amplitude vector capital Y for this output y, then we can show that this y is between the maximum and the minimum singular value, and this is all for a particular frequency, and this holds for all omega. And in order to just understand these things better, I have hard coded this. So let's have a look at the Matlab code, which tries to show that numerically for our example. So in this script frequency analysis, we have a section here that is on the screen. We first define the transfer functions. So because GYR is in a state space form, we convert this to a transfer function form here. And now, in spite of having the command sigmas, in order to just understand sigma plots better, we do this manually here. So I grid the frequency axis omegas from 0.01 to 100, and at each frequency I get g of j omega here, which are the frequency response matrices. Now for each frequency omega we do an SVD, and from the diagonal sigma matrix, which is here SSS, we get the maximum and the minimum singular values. Then we plot it on a log scale to obtain these plots. So here you see the minimum and the maximum singular values for each omega. So now let's look at the outputs for three different canonical directions that we saw, or that are used for the border plots, and this we plot here. So these are the sigma plots, and now for the first canonical direction, we get the output as shown now with the red. You can see that that is clearly contained inside the sigma max and the sigma min plots. Now for the second canonical direction, we get the other red curve, and finally for the third one. So one thing I should note here is that this is true for g square, or in other words, if we have the same number of inputs as outputs, which is the case for our closed loop system. So now in this code, WRC15 LQG sigma, you see the model defined again with the same function. Then we get the state space matrices. We then have the two designs, design 1 and design 2, and we build the generalized plant here, as can be seen in this description in the comments. Then we design the two controllers K1 and K2 using the h2syn command, and then we plot the singular values for these two designs. So this figure now shows the two designs here, and the singular values of the sigma plots for these two designs. Now let's first see or compare the two designs. So QE is generally BB transposed, so it's 2BB transposed here, and QE here is 50 BB transposed, and the Q here is generally C transposed C, and the Q here is 50 times C transpose C. So let's first look at what this means. The R's, note that the RE and the R for both designs would be the same. Now this one first would mean that for design 2, performance is more important than control effort. Or in other words, control is cheap. So the optimal controller would try to use more control input than in design 1. Now so this is based on Q comparison. Now again, by comparing the QEs, what we see is that the REs are the same, so QE for design 2 is much higher, which would mean that we have a much lower measurement noise for design 2, which would again mean that we can have, or we can trust the measurements, and therefore have a fast observer dynamics. So with the combination of these two things, we would in general have a much faster controller for design 2 and a much faster observer for design 2. So let's look at the sigma plots now. We see that for design 2 we have at low frequencies quite good tracking performance, and that is because at low frequencies the sigma max and the sigma mean values are quite close to 0 dB, which is 1. 0 dB is nothing but 1, which means that at low frequencies we have for any direction, not just the worst and the best, but any direction, we would have a reasonable good tracking for design 2, whereas for design 1 we have sigma max and sigma min much further from 0 dB than for design 1, which would mean that we have, as compared to design 2, a poorer performance in tracking for design 1. Now if we compare the frequency regions here, we see that design 2 will fail to track inputs with frequency ranges somewhere here. So for example, frequency of 10 radians per second, for an input frequency of 10 radians per second, design 1 will fail to track, whereas design 2 will be able to track an input of 10 radians per second. The drawback of design 2 would then be seen for higher frequencies, which is here. If we have noise, design 2 shows a higher sensitivity to noise because the sigma max, so we have one direction such in which if we have a noise along that direction, output amplitude would be here, whereas for design 2 it would be much lower. So overall that means that design 2 is faster and shows better tracking performance in the low frequency regime and the mid frequency regime, but at the cost of showing a poorer disturbance rejection or a high sensitivity to noise. And so that was basically it for this problem. So that was the interpretation of singular values. Now 14.1 is basically just the same for any LQG design, so we consider that as being done as well. Now for the last one, we have to plot the singular values of the sensitivity transfer function. So let's first quickly recap what is the sensitivity for a given loop of this form. So the sensitivity or the loop sensitivity denoted by S is the transfer function between or from R to E. So we see that E is nothing but R minus K G E. So that just means I plus kg E equal to R, and if I invert this, get this, and this thing is called the sensitivity. So here you see now the sigma plots for S, and remember that S is the transfer function from R to E. Now note that the difference between sigma max and sigma min for low frequencies is huge for this example, which means that along some directions, so let's write this as follows. So there is a U max at low frequencies. So for low frequencies, omega sigma Vmax, and S of j omega U min is sigma min V min. So sigma max is around 10 dB and sigma min is around minus 70 dB. So what this means is that if I have an input sinusoidal, if I have a sinusoidal input along Umax direction, my output will be along the Vmax direction, sinusoidal, because it's a linear system, and with an amplitude of 10 dB, and my output in this case is an error, so I will have a large steady state error along this direction. On the other hand, if my input is a sinusoid along Umin direction, note that Umax and Umin, Vmax and Vmin are all 3×1 vectors here. So if I have a sinusoid input along the Vmin direction, my output would be minus 70 dB, which is quite small along the Vmin direction, and so my error would be quite low, and here my error would be quite high. And this you can see in the Matlab code by finding functions. So here you see the Matlab code. You can get the best direction, which is the direction corresponding to the smallest singular value, and the worst direction, which is the direction corresponding to the largest singular value, and then simulate your system to get this response.